x squared plus 2x plus c, and this variable is unknown. So when you integrate it back, so this is a differential equation. Differential equation is an equation that involves derivatives. And when you try to find the original function, there's always this problem. You don't know what the original c is.
Right.
So initial value problem is one way of figuring out this value here. If you're given some condition, you can always plug it back here and figure out the original equation. So we've got this differential equation here, and the easiest type is first order separable ordinary differential equation. This is the easiest type. Okay.
Yep.
There is first order inseparable cases. I'm not sure if you've gone through that. Have you?
What is it?
Yeah, there's there's first order inseparable ordinary differential equation. So that involves integral factor.
I don't think we know that.
Yeah, so you guys may go through that maybe next week. I'm not sure. But in many cases, like in engineering and physics, etc., most problems, they cannot be solved by hand like this.
Yep.
You use this numerical method. So people rely on computers to solve it for them. And some case like this is really, really special. Okay, so you have dy dt equals negative y squared over t plus 1. So for the first question, I think you guys already went through this. Swap that and put that over here. Yeah, dt over here, then you get this. You integrate both sides. And you get this, and then you get that, and then you get that. And you plug in these initial values. So these are the initial values. So you can see that. One thing that I would like to mention is that when you integrate some hyperbolic functions like this, you get ln, and it must be absolute value here.
Yep.
Okay. Otherwise, it's wrong. And your teacher only has this round bracket. So I think that's something that we need to talk about.
Right.
Okay, so you got 1 over y equals to ln absolute value t plus 1 plus c. You plug in 0 and 2 here, so you get half equals this. So ln 1 is 0, so you get half. I'll later send this picture to you guys. Don't worry about writing it down, okay? Just try to understand as much as possible if you haven't done this question. And 1 over y equals to therefore this one plus half. We found the c. And well, there are a number of ways of doing this. One method is I times everything by 2y. So you times it by 2y, then you get 2y here, 2y here, then you get y, 2, and 2y like this. Factorize and divide. Okay.
Oh, okay.
Another way is, so when you get to here, just flip it. You get y equals to, and then you flip that, you get 1 over ln t plus 1 plus half, and then you times everything by 2. Then you get 2 over ln 2 t plus 1 plus 1. Okay, so that's the answer. Now, I have some issue with this wording here. It's not a general solution. So general solution is a solution. This is general solution here. This one here. You see how this still involves C? Yeah?
Yeah.
So when you integrate that and then you don't plug in any initial values, then you get the general solution. So general solution involving constants. or coefficients. It is only when, so when you integrate it, you may get some solution like that, or like that, or like that, or like that, or like this, or like this, or like this. But then you say, if you mention that it goes through that particular point, then you are fixing your answer to this one. So all of these are general solutions, right? And as soon as you plug in the initial value or a particular point, then you arrive at this particular solution. This is a particular solution.
Okay.
Does that make sense to you?
Mm-hmm.
So I don't think this is a right way of saying this. So this is a particular solution. I want you to go and check with your teacher.
Right.
Next week, just tell him, shouldn't this be a particular solution instead of general solution? Now, another thing that I wanted to go through with you is t plus 1 there. So let's actually go to GeoGebra and see. So we've got y equals to 2 over 2 and then ln 2 times ln of x plus 1, was it? Plus 1. Okay, so we've got solution like that.
Mm-hmm.
And as you can see, this function is not defined for, because log, inside of log, you can never get negative, right? So if you get x equals negative 1,
Yeah.
that's that line. And if I change this to absolute value of x plus 1, did it change that or no? It should be also available for, okay, so I think we have to put a bracket there and then absolute value. Okay, there you go. So because it's absolute value, it's giving us the mirror image of the original solution, right?
Mm.
It's not only giving us that and that, but also giving us that and that. Mm-hmm.
Right.
So let's talk a little bit about the background of this. When you have 1 over x, it has this, right?
Yeah.
And when you integrate this one, what do you get? When you integrate 1 over x, what do you get?
ln x, right?
ln x, right?
Okay.
ln x. So if you write ln x, it's only giving you 1/2 of it.
Right.
What about the integral of this one? You see? So you can see that if you look at the purple, the gradient of the purple is given by this one.
Right.
Mm-hmm. But so gradient of this one, there's another one. So if I write absolute value of x like that, see the gradient of the purple is given by this one here.
Mm.
It's always positive. Gradient is positive, but this one has a gradient of negative, right?
Yeah.
Yep.
So the gradient of this purple here is given by this one. So that's why integral of 1 over x is ln absolute value of x. In a similar way, integral of 1 over t plus 1 must be this one here. Mm-hmm.
Mm-hmm.
And this question doesn't say that t is defined for t greater than -1. It doesn't say like t must be greater than -1.
Right.
If it did that, then this would be the answer.
Mm.
But
But if it doesn't have that, it must be this.
square bracket?
Not square bracket, the absolute value.
I mean, absolute, yeah.
Yeah, if that's what you meant.
Yeah.
So I think that must be the answer. So I want you to go and check with your teacher about that as well.
Mm-hmm.
Okay.
Yeah.
Yeah. But it would be, so if t is greater than -1, if that's the condition, then this would be the answer.
Right.
Because when t is greater than -1, this value is going to be positive anyway, so you don't really need the absolute value sign, right?
Yeah.
So
Yep.
that's another thing that I wanted to check with the teacher. All right.
Right.
Now, so assuming that t is greater than -1, and this is positive value. So if it's positive value, then this is the solution. If let me write it here. If t is less than -1, then then your answer must be changed to 2 over 2 ln and then 1 minus t. Negative t negative 1. Sorry, negative t negative 1 plus 1.
Okay, yeah, makes sense.
Yeah, because you know, absolute value of t plus 1 is t plus 1 if t is greater than -1, and a negative t negative 1 if t is less than -1, right?
Yeah.
So just yeah. Now that's the answer for B.
Mm-hmm.
Did you get the same thing?
Yeah.
Yep, we got that.
Okay. Now we got this. Let's go through this one first. So if you have this differential equation, and it goes through t naught, while there are many techniques to find exact solution, there is still a wide class of first order different that must be approximated by numerical methods. So what it's saying is this: there are many, many techniques that can give you the exact solution, which means you can solve by hand. But there are a lot more that can only be solved by numerical methods, which means by computer, such as Excel or Python, whatever. So we're going to use Excel today, okay? Because you guys all have Excel. Have you guys heard of Python?
Yeah. It's the
So this is Python, right? Here.
Huh.
Yeah, I'm just doing some stuff for my work.
Wait, can you guys hear me now?
Yeah, harder.
Hey, Rev.
Yeah, hello. Okay. I can hear you. Right. So anyway, so Python is actually the most popular computer language these days. I strongly recommend you guys to all learn Python if you're going to do any like science, STEM related major in uni.
Yep.
Yeah, everyone's doing that these days. Oh, by the way,
Can we use Excel for this?
Yeah, we can use Excel for this. So it's right here, okay?
Yeah.
So what it means is this: if you have, so one method is using Euler's method, which is given by this here. Do you guys know the meaning of this?
No, not really.
Not really?
No.
All right, so it's very, very simple. So when you have dy dx equals to some function, so I'm not going to write this as f dash, I'm just going to write it as xy. So what it means is that's the gradient function, okay? Let's actually write it as a f dash. So usually f dash is given by f, usually you wrote f dash of x, right? And this one, the gradient is given by, let's say, for example, 2x squared plus 4. Then you can figure out the gradient by plugging in some number there, true? So plug in 1 there. And the gradient at 1, for example, at 1, I don't know what the y value is, but let's say y value is here, for some y value. The gradient is, that's the meaning of it. But now, what if I have f dash of xy? So that means the gradient is now given in terms of x, also y. So this is actually like, could be like y sine of x over 2 plus y squared. So something like that as well, okay? So the gradient can be given by x value only, but it can also be given in terms of with the y value as well. You need both x and y value, okay? So we call this one explicit case. This one is implicit case. All right. So let's suppose that the gradient is given by this function. Now, when you start from here, this is xn minus 1, and let's say this is yn minus 1. And let's plug that into this gradient function. So f dash of xn minus 1 and then yn minus 1, that's going to give you the gradient, the instantaneous gradient at that point. Is that right?
Yep.
Let's say at that point, the gradient is like this. So let's say the actual function looks like this. So let's say the actual function kind of goes like that. So this value here, so this, let's say this is an x of n, then and this value here is the y of n, right? But what happens if I do this? F of dash of take a look at this. So this is the value that I want to approximate. This is the actual value. When you plug in xn, you get yn. But using this formula, we can approximate. So y is approximately given by
I can understand.
minus 1 plus, so that value plus this value here.
Mm-hmm.
But since rise over run is the gradient, so you multiply the gradient by this gap here. So I'm going to call that h. You multiply that by h. So because rise over run times by this gives you that, right? Because
yeah.
So that's the rise.
Run.
So the gradient times by the run will give you this rise. And then you add this rise to this y value, then this value, this one here will give you that point, whereas that point is the actual value you want. So of course you are actually a bit short, but if you make this step short enough, then you go a little bit to the right and then you approximate that value. And then you do that again, you go a little bit to the right from there and approximate that value. So you can get very, very, very close. If you do this like at infinitesimal step, you can approximate this really, really accurately.
Okay.
Does that make sense to you?
Yeah, that makes sense.
So here's the function. And I'm going to start. So you see how this function says that the initial value is 0, 2?
Yeah.
Mm-hmm.
So we are starting, actually, let's have a look at, so this is t, and this is the f of t.
Yeah.
So we already found the particular solution, right?
Mm-hmm.
This goes through 0 and 2. So if I plug this value into here, and here's my my formula.
Yeah.
2
Do you want us to get on to Excel right now, or
sorry?
Do we have to get on Excel right now?
You don't have to. Just watch this. I'm going to send it to you later, okay?
Oh, okay. Yeah.
So this is the formula, and I'm just made this into 2 over 2 times natural log of 0 plus 1, close bracket plus 1. Then obviously it gives us the initial value 0, 0, 2. I'm going to scroll it down.
Mm-hmm.
So scroll this point here and then scroll it down. It copies the formula. So it plugs in 1 there, 2 there.
Yeah, yeah.
And I'm going to do it up to 9. But I'm actually interested in this point here. So it's like 0, 1, 2, 3, 4, 5, 6. But then this is the e square minus 1, which is actually the value that we are interested in, e square minus 1, right?
Mm-hmm.
Mm-hmm.
So I think what the question is trying to say is, so this is not an approximation, guys. This is the actual function. Let's take a look. So, okay, so that's sort of what it looks like. Okay. So here's the 0 to 10, and this is what I want to know, right? This is what I'm trying to approximate. Okay. Actually, so I'm going to change the type. Change the format of this. Actually, let's not graph it here. I'm going to do it on GeoGebra. Yeah, I already done it here. So I'm only interested in the x+1 case, not the absolute value. So that's what I want. And when I plugged in the e square minus 1, this one here, I got 0.4 exactly, right?
Yep.
0.4. So I'm gonna go here and then type e square minus 1 and 4, 0.4, sorry. It is right there. It's right on the point, right? What I'm gonna do is I'm going to start from here, and without using any integration result, the aim is to get very, very close to this one, okay?
Yep.
So take a look at this. I'm gonna write, okay, so this is now approximation. T equals to 0, start from there, and of course, my y value is 2. Now, I'm gonna now go for 0.0001 maybe. So this, I'm choosing my step to be 0.01 and then 0.02. Let's scroll it down to about 6.4, okay, 6.38. So scroll down to 6.38. Okay, that's enough, right? Now, my approximation is I'm starting from here and then plus the gradient. The gradient is given by, if we go back to this, so this is the gradient, right?
Yep.
So let's actually write it down. So the gradient is negative y squared over t plus 1. What's going on? So that's my gradient. And just ignore this part. We are not cheating by looking at that. So all I'm given here is the fact that the gradient is this, and I have absolutely no idea what my y value is because I haven't integrated. I don't know how to integrate. And all I'm doing is relying on the Euler's formula. And the Euler's formula was y equals to y2 equals to y1 plus the gradient that involves x1 and y1 times by the h, which is the step, okay? So how do I figure out the y value when t equals to, so in this case it's t. So, all right, so this is my previous y. This is the previous y. plus the gradient. The gradient is given by this one here. It's going to be negative of the y square, this one square, and then over t plus 1, which is, of course, the original, the previous t, plus 1, and then times by the step, which is always 0.01. Does everything make sense to you?
Mm-hmm.
Wait. Mm-hmm.
But I think I have to close the bracket here. Any question here? I can go a little bit slower if you want.
No, it's good. Yeah, I understand.
You have to close the bracket at the end because it's still coming in red.
I don't have to here because this bit is the gradient, right? So let me actually write like this is T1, this is T1, and this is a Y1. Okay, that's T1, that's Y1. This is T2, this is Y2. Okay, so Y2 is given by Y1. All the formula is gone now. Let's try again. So Y2, that's what I'm trying to do, is Y1. This is Y1 plus gradient. So gradient will go into this bracket times by the step. Step is, in this case, 0.01. Okay. Or you can write this as that minus that. Okay. Hold on. Why is it not highlighting? Oh, there you go. Now, and so that's the step, and the gradient is given by this one here, which is negative y. So this will be the y1 square. So y1 square over bracket t plus 1, which is that, plus t1 plus 1. Okay. So I've got 2.04. And all I have to do is scroll this down. So if I go for next one, you can see that this one is using that number as the y original. So we're trying to figure out y3 now. y3 will be y2 plus grad t2 comma y2 times by the step. So that's the step there. This minus this is a 0.01 here. And this will be the previous y square over this one plus 1. So that's t plus 1. And adding on to this one. So you can just scroll this down. Then you can get up to, so you're just using, oops, what's going on? Why is it getting so big? It's supposed to actually go down. Hold on. That's negative y square, and then t, that's right. It is supposed to go down. Why is it going up? Do you guys see any mistake? So the gradient is given by y square t plus 1.
Do you need to put y1 in the bracket if you square it, or like put the square in that y1 and then put the negative out front? Or is it making it positive when you square it?
No, you're not making a square when you square that. Maybe put a bracket around this one.
That's what I mean.
Yeah. And maybe you can put this negative at the front, like that. That's the gradient times by, yep, that's right. Oh, it went down. That's what you're supposed to scroll down, yep. So I don't know what went wrong before, so it's going down, right?
Mm-hmm.
So you can see with the approximation only, you can see that when I go to about, so the value that I'm trying to approximate is that point. Where'd it go? Yeah, this one here, which is when it's about 6.39, it's supposed to be 0.4, right? Let's see how accurate this approximation is. When you scroll down to 6.39, that's very close to 0.4, isn't it?
Yeah.
Yeah. So this is the method. You can also do, so I'm going to copy this and make it 0.001. So I'm making my step even finer here, and 0.002. And if I scroll that down.
Yeah, I think the question's asking for the number of steps that produces the result. So
yeah,
so it's asking for, I think, how fine the increment is.
Yeah. Hold on, what's going on?
No, I think just select and then just drag down should work.
If I drag down, it's gonna take too much time.
Oh yeah.
It's gonna take way too much time. That's why. So if I do that and do this, oh, copying 0.1, what the hell? So is there a faster way of doing this?
I'll try looking it up.
Oh, bloody hell. Give me a second. So if I do 0.001, 0.002, 0.003, and that one is taking that value and then negative that one square plus that one plus 1. That's right. That's the gradient plus the step. Step is given by this. I'm going to change that to 0.01, 001. Just fix that. And if I scroll this down, no, that's not working. Scroll just this down. That's fine. So if I scroll these down together, no, it's not working either. So it's really annoying. 0.004, 0.005. What's that noise there? Were you watching Excel video?
Yeah, sorry.
Oh, this is so annoying. No, I can't do
you can do wait. So go to sort and filter.
Mm-hmm.
You know that. Actually no wait. Oh no. Oh, you know fill. You know next to auto sum, under auto sum, there's this thing called fill.
Mm-hmm.
Yeah. How do we sort that?
Yeah, that's what I was trying to do. So if you do that with the fill, it's all filling it up with that. Oh, I've got an idea. So actually, 0, 0.001, 0.002. So that one is that one plus 0.001. There you go. And then you scroll this down. Hold on. That one is that one plus 0.001. So you scroll this down. So it is working. And then do that to that's gonna take a long time. There you go. Okay. So what I did here was, so I can show you. So you select a lot,
Mm-hmm.
and then just press Control down.
Right.
Okay, Control down. Then you can replicate this.
Okay.
Now, I'll just do this now, and scroll this down to. We just need to go up to 6, right? Just up to 6. Let's just do it up to here. Control down. There you go. So you can see it's going down, and so it's a lot finer step. So I need to go down to 6, right?
Mm-hmm.
6.39 it was. Okay, so when we look at our value, it was, so if you type a, where is it? A to the power of 2 minus 1, you get 6.389. So we're gonna go for 389. 389 right here.
Mm-hmm.
So that's pretty close to 0.4, right?
Yeah.
So 0.4 was actually right there. So we're
Right.
off a little bit. So that's the method, but let's have a look at this question and see what it's looking for. It's a little bit ambiguous what they're saying. So using Euler's method and the computational tool of your choice, find a number of steps. Number of steps. So are they looking for the H or the number of steps, which is like if you have H equals to 0.1 and you're trying to approximate at t equals to 6.389, then you need how many steps? 63 or 64 steps, right?
Mm-hmm.
If you have H equals to 0.01 and t equals to 6.389, then you have to do about 638 or 639 steps, right? Etc. So in the case, this is about 6,400 cases steps, right?
Mm-hmm.
If you want to go even finer, then you'll have to go 6,400 steps. So this is my first question. So what is the number of steps that produces a result? And here, what result are they looking for? So see how I started from there and ended up over here, right?
Yeah.
So do they want this result? I'm not even sure about that because it's what is the result? See?
Yeah.
It's like completely disconnected question from the previous two. That produces a result.
I think they mean the points, like, you know, the
Okay,
coordinate.
so when rounded to 3 decimal places, agrees with the exact solution. So do they want us to approximate from there to there or from there to there? It doesn't even mention that.
I think maybe it's connected to B, where they're looking for the point at which.
Well, they should have specified that.
Yeah, I don't know. Like, it's very vague. This whole assignment was pretty badly written.
Yeah. This is find exact value of this, right? So probably the exact value that they're looking for is this.
Yeah.
They should have mentioned to us where you start. See?
Yeah.
You could start from 0.2, or you could start from somewhere else, you know?
Yeah.
You could start from there and approximate that one, right? So, so actually, the only point that we know is this one. So I think it's a good assumption to assume that if we're starting from there and we're approximating this one.
Yeah.
I think we should specify that as well.
Yeah. All right. I think it would have been better if they say find the step size, the size of the step, not the number of steps. Okay.
Right.
Yeah, because it's really the h. But anyway, we can tell both. Okay. So when rounded to 3 decimal places agrees with the exact solution, you must attach spreadsheet. All right.
Yeah.
Now, so if we look at this one here, when rounded, you can see that it agrees with the 0.4, right?
Yeah.
But when you look at the other one, this one here, 0. We can. So this was about 600 something points, right? Hold on, that's way down. So let's go down to 6 point something. 6 point, this is the closest value, right?
Mm-hmm.
When it's rounded, it doesn't quite agree.
Right.
It's not 3
Does
points.
that mean we need a smaller step size?
So we need smaller step size than 0.01. So when we did 0.01, it doesn't agree, right?
Yeah. Oh, okay.
Yeah. So we can write the Excel shows that. So we know that e squared minus 1 is 6.3.
89.
Was it?
Oh wait, the actual value is 89.
Yeah, 89. That's right. And it gives you y equals to 0.4. So that's what we want to do. F of e squared minus 1. So Excel shows then when the h is equal to 0.01, F I have to be careful about how I write this. When the step size is this, when t equals 2, you can only, because the step size is 0.01, you cannot say t equals to 6.389. You can only say 6.39, right? Which matches that digit with this one.
Yeah.
Then the y value was how much? This one here. 0 point that. All right. Now, when h was 0.001 and t equals to 6.39389, the y value, I have to say here, y value is approximately, okay? It's not, it's actually 0.4, but. So when this is rounded to third decimal places, it's equal to 0.398. So when this is applied, we found that it's 0.399, what was it before? Yeah, we scroll down to about 6,000. Sorry. Oh, that's way down. So we scroll down to about 6,400. Okay. Was it this one? 389, was it?
Yeah.
Yeah.
This one here. So if I go for more decimal places for that, so that one there, is approximately this,
Mm-hmm.
Which is
approximated to 0.3.
0.4.
Yeah, when it's rounded 0.400.
When it goes
400, that's right.
Mm-hmm.
Yeah, that's rounded. But is there a way to figure out, so this was not enough, but this was enough, right?
Mm-hmm.
So is there a way to find maybe somewhere in between those two? 0.005? Would that work as well? See?
Mm.
So how do I do that? Is there a faster way of doing this than trial and error? That's something to think about. I think that might involve me using Excel solver button. There is, if you can see, as a developer, and there's actually data. Was it data? I don't know. Developer, I think it was. Where's the solver button? Oh, there's macro, review data. Do you see solver? Home, help draw, page layout, formulas, data. Yeah, there is a solver button. I can't really see it. But if you want, you can try with, so because we know that the answer is between those two, right?
Mm-hmm.
You can try 0.002 and see if it works, right?
Yeah.
We can actually give it a go and see if it works. So we're going to go for approximation here again with the t equals to 0, and then this is 2 here, y value, and I'm going to copy this one, this formula, and just move that over here, move that over here, move that over there, and the step size is 0.02. And you can see that's different from that one, of course. Actually, 0. Was it 0? Oh, hold on, 0.001. That's right. Now this is 0.002, and now this is 0.002. This value is that plus 0.002, and scroll this all the way down to the bottom. Down. Just taking a bit of time. And so step size is a little bit larger, and that one there is that one, and let's just scroll this down. Then you get this one is equal to that one, yep, I think that's all fine. So we have to scroll this down to about 12,000, oh no, 3,000, right? Because step size is a bit larger. So about 3,000. It was 6,400 before, so 3,200 should be enough. Yeah, around here, right? Okay, so I can see.
Yeah.
6.388.
So it's 1 off.
Hold on, why is this one 3? Oh, that's right, yep. Which one should we take? We're looking for 389, was it?
Yeah. Yeah, that's fine. I think we can play around with that like one.
So I'll leave this one to you.
Yeah. Have you? So with question 2, we were like just wondering about.
Okay. So let's go through question 2 now. So I'm going to save this.
Yeah.
All right, question 2. Oh, where'd it go? All right, question 2. So consider a second order ODE. I think there's a bit of a noise coming from one of you.
I think it's Vishal.
Okay, so consider a second order ODE from the form of this. All right, with y dash, so that's the particular point. So what this is saying is that, you see how this involves a double derivative? So if you integrate that and then you find y dash of t, and then you integrate that to find the y of t, but then when you integrate that, you're gonna end up some expression with the c there, right?
Yeah.
So to solve for c, you plug in some particular point t naught, then this will be something plus c, but overall this will be y dash naught. It will be some particular value. So from there, you figure out the value of c. And you plug it back here, and then you integrate that again. And this will be some answer with d, and then you plug in y of t naught, so same t naught there. And of course, this will be some value plus c. And then and this will be some y naught. And from there, this is actually d now. And from there, you figure out d. Okay, so that's why they're giving you these two values here.
Oh, okay.
So IVP, rewrite the IVP as a pair of first order IVP using the transformation y dash equal v, and hence describe an algorithm for finding an approximate solution to original IVP. So they're not giving you any value here. Have you guys gone through reducing second order into first order?
I think I've done a bit of that.
A bit of that. So let's take a look at an example. So reducing second order into first order. Have you got a canonical form?
They give us the form they wanted in, which is y dash equals v.
Y dash equal v, that's right.
Yeah.
Sorry, just give me a second. I haven't done this for a while, so.
That's all right.
Okay, second order, something like that. S is equal y dash, so that's right. Yeah, reduction of order. So it's of this form, that's right, equal 0. Then you can do general solution to this, given that. So you have C solution. Y1t, so Y2 equals that. Okay, so for something like that, you have, so we can go a little bit over 1 hour, that's fine. So once we have this, Right, so you're letting this equal. Yeah, reduction of order. So whenever you have that, product for that, double derivative. Yeah, that's the integral factor there. All right, back to this one here. So do you guys know how to do A here? What did your teacher say for that question there? Your teacher mentioned something, right?
I think it just changed the equation.
That's for 2B though, so that's
2B.
2A's are unaffected.
2 is unaffected.
2A is unaffected. Yeah.
He made the question into y double dash minus 3y minus 4y.
Yeah, so yeah, this is the updated version. Yeah.
And the solution is for when t equals to 2. So
Oh yeah, that's what it's changed. Yeah.
Okay. All right. So when you write y dash as v, so that's going to be v. And this is going to be v dash, right?
Mm-hmm.
V dash plus pt, and this is v plus y. It's going to equal to, what's this going to be? Has anyone done A?
No.
No.
Vishal? No?
Oh, no, I haven't done it yet.
Okay, so let me get back to you on this. So it's talking about algorithm, okay. So use algorithm from A with 100 iterations. So they only want us to do 100. Find an approximate solution to this initial value problem involving this 2 here and this here, okay. Correct to 4 decimal places and hence calculate percentage error given that exact solution for this is approximately, okay. Right. Okay, so we'll have to do A first and then the computer to figure out. Get this down to the first order. So because from question 1, we know how to do this if it's a first order, right? If it's first order, then your y equals to, you know, previous y plus the first order differential times by the h, right? And if it's 100 iterations, then divide 2 by 100. What do you get? You get 0.02, right? So your step here is going to be 0.02. So you start with 0, and then 0.02, and then 0.04, etc., all the way down to 2. Okay? And you compare that answer with this one. Okay? So it's all about just getting it down to the first order. Okay? Now, let me do a little bit of research. If you guys have time to hang around, that's fine. I'm not going to charge extra money for going a little bit over. So the aim was to finish up the question 2 today. Reducing second order into first order.
I think you just find the derivatives of so the integrals of both sides. They should work for me.
No, it's actually quite different from just, it's not as simple as integrating both sides, no.
Okay.
So this is second order. So usually what we do is write this, so this is W, so differential equation, okay. There's an integral factor. You guys haven't done integral factor, have you?
Sorry, what was that?
We've done that.
Yeah, we've done
that in class.
But that's for first order, sorry. That's for first order, not for second order. That's type 1 second order equation with a dependent variable. Characteristic dependent. So y dash equals W. Hold on, just give me a second. I'm just going to turn up my heater. It's too warm here. Okay. Yeah. I think this. I think my memory will come back soon. So just give me a second. So second order equation. This is a homogeneous equation. So yeah, that stuff. Does this one look similar to that? Y double dash this and this. So that 3 of that, right? This one is homogeneous. This one is not. So this one is just x here, whereas your one here is another function. So this is not homogeneous case. So this one is homogeneous case. On method of undetermined coefficients. So that one there is with y double dash y, and there's another function there. No, I don't think this is the method that we are looking for. Yeah, variation of part, maybe this one here. That one there, and it shouldn't be too hard. Oh, maybe this one, reduction order. The defining characteristic is the dependent variable y does not explicitly appear in the equation. This type of second order equation is easily reduced to first order equation by this transformation. So this is, in our case, that's V. The substitution obviously implies that y double dash is V, y double dash is W dash, and the original equation becomes the first order equation. So here's an example. So this one simplifies down to why is it W here? W. So the y is missing. So y dash equals W, y double dash is W dash. And so this, I think this is what they meant there is X here. That's why it was confusing. So it becomes this, which in the standard form, applying the method of solving such equation, the equal factor is first determined. So if you have, that's right. So we have, so you guys have to know integral factor. So reduce this to this one here, and the p value is just a 1 because that's 1 here. So integral factor is e to the power of this, which is e to the power of x. Multiply e to the power of x here, here, here. Then you get this, and then you make it into this form here, and then that becomes, it's solvable. But you don't have to do, maybe you don't have to do the integral factor because we'll be using, we'll be using numerical method. Okay, so you get that, and then you plug that back in here, and then integrate that again, then you get the y value. Right, and then another example is, this one still doesn't have the y, so we're gonna skip that one. But another case, example 3, it still doesn't have y. Is there another example? Yeah, this one's got y there. So this one is w to the power of 3, and you have w, y double dash is that. Transform this second order equation into first order. How did they do this? So y square, and therefore you get this. It becomes a separable equation. Right. So these are all exactly solvable. Y dash. Okay. I'm just going to let this equal 2. Instead of doing 1, I'm just going to try B straight away and see if it works. So this one's our V of T dash, because we're writing this as so Y dash equals V, so Y double dash is equal to V dash. So this one's V dash minus, and this is a 3V minus 4. We don't have to write this in any other form, so you get that, okay? Does that make sense to you?
Yep.
Mm-hmm. And from here, so this is dv dt minus 3v. So v is actually y dash. So we can rewrite this as 3v plus 4y. So that's our derivative equation. So we can first do 0, 0.02, 0.04, 0.06, and we can do v here. So you can see that because y, we have this situation, y is 1, and y dash 2 equals to negative 26 over 31, which means this one is v, isn't it? Y dash is v.
Oh, why'd you make it equal to 0 with the v dash t equation when
Sorry?
it's equal to, you know how it was equal to gt? Why is it equal to 0?
Yeah, gt is 0 because in this case it's 0.
Oh yeah, sorry, yeah.
Yeah, do you get it?
Yeah.
Yeah. So later I'm going to show you how you can solve this exactly. I think this is exactly solvable. Okay.
Right.
Yeah, but we're just going to do, so I think part A is going to be difficult to write because you see how all these things are like in terms of variables, P and Q and G of T, and this is T naught Y dash. So I think this is going to be quite difficult to, they're asking for algorithm to do it. But I'm just going to go straight into this question. So I wrote this one as V dash and this one as V dash, a V, and this is just a Y. And I rewrite this one so I get this first order. You can see that this is first order differential equation, right? Why is it first order? Because there is no second derivative.
Mm-hmm.
And Pretty much. V dash, sorry. So y is another variable. So I'm not sure actually if this is right, but let's just try, okay? So we're given these initial conditions. So that also means v of 2 when t equals to 2 equals to negative 26 on 31. Got it? And did your teachers say change this value at all? Because if we're given the initial value at 2, that's just equal 1, right? Y of 2 is 1. So it must be 1, right? So did he change that value as well? Guys, are you there?
Sorry, what?
I'll check the email.
Let's read his
It says,
comment.
and the solution is for when t is equal to 2.
So your teacher said what? So ODE has become this, and the solution is 4 when t equals to 2. Okay. Maybe this stays. And the solution is for when t, solution is for t equals to 2. Oh, yeah, this is a changed version, isn't it? When I'm going to check Ravin's question, Ravin's, what he sent to me. So the previous version is when, it doesn't say that. It doesn't say t equals to 2. So everything stays the same. So this value here is 0. This is also 0. So this is 0 here, 0 here, 0 here, 0, 0, 0, okay? Now, what we need to do is figure out v from this and then figure out y later, I think. Because v is the derivative of y. V is the derivative, yeah, okay, sure. So from this, I'm going to actually just copy this down onto my Excel and actually start a new Excel. All right, so I've got t, I've got my v. So t is 0, and it says that the initial condition is when 0, v is negative 26 on 31. Negative 26 on 31, okay. Next, if I go to 0.02, and I could scroll this down to 2, right? When it gets to 2. Right? Then you can see that my v let's think about this. Hold on. That's the gradient. The gradient is given by that. Now, using the Euler's law, it's the original v plus, remember how it was gradient times by the h? And h is 0.02. And the gradient is given by, as you can see, 3 times the v, 3 times the previous v, plus 4y. Hold on. What was the y value? The y value is 1, right?
Yeah.
Yeah, but for the next one, it's going to be a bit difficult because you don't know what the y value is. Okay, so we're going to have to do y here as well. Y value. So when t equals to 0, y value is 1. So this one is actually y dash. This one's same as v. Okay. So now y value is equal to the previous y value plus the y dash. Yeah, that's right. The gradient. That's right. The previous gradient. That's right. This one here times by 0.02. So that one's based on that. That one's based on that. So I'm going to scroll. So none of these are depending on the x value, a t value. Hold on. Let's see what happens if I scroll it down. I got negative 93. That's pretty similar to this one here, but it's negative. Okay. All right. So what I'll do, guys, I'll figure it out tonight. And shall we have another tuition tomorrow to go through question 3 and 4 as well?
Yep.
Yeah, let's just finish it up
So
tomorrow.
let's just call it a day here. I'll figure this one out and let you guys know tomorrow, okay?
Okay.
Yep.
I'm just gonna charge you total 2 hours for this whole assignment, okay?
Right.
Okay.
Even if we take a bit longer, maximum I'll charge you is 2 hours. So,
Yeah. Okay.
yeah, it's gonna be something like that, okay?
Right.
Yep.
So yeah, we'll call it a day here. I'll see you guys tomorrow.
Okay.
All right,
Thank
see
you.
ya. Thank you.